Welcome to the video for section 2.7, which is position vectors. Learning to generate a vector that represents the position of a point. And that could be a point relative to the origin of a coordinate system, or usually it's the position of one point relative to another point. So we have a vector from one point to another point. And this is useful in statics because typically you're not given forces in vector form. Instead, you're given the geometry of a structure, and you know the force in a member. So, for example, say you have a beam in compression. You have a blueprint of the structure, so you know where the beam is located. And again, like I said in the previous section, you'll want to find a vector that represents the compression force. So, in order to do that, you get a position vector representing 2 points on the beam, and then find the direction of that, and then multiply that by the magnitude of the compression, and that'll give you a vector for the force. Or likewise, if you have a rope connecting two objects, you know the connection points for the rope, and you want to get a vector representing you want to get a position vector from those points to be able to represent the tension as a force. So the first step is getting those force vectors is to be able to have a position vector. So looking at the figure, we have 2 points, point A and point B, and position vectors. We'll represent those with an R typically. So RA and RB. And if you look at the figure and the vector addition, we see that RA, the vector RA, plus the vector R, as it's labeled in this figure, is equal to RB. So the head of RA, and then connect the tail of R, and then the head of that. So the tail of RA to the head of R gives you RB. So hopefully you see the vector addition there in the figure. And we'll use this equation here to get a definition for the vector from A to B. And, just for clarity, the vector RA is defined as RAX in the I direction plus magnitude RAY in the J direction plus magnitude RAZ in the K direction. Okay, so using this, and this is the same thing for RB, we just substitute RBX. In this equation, we will get, vector R is equal to, okay, well, let me rewrite this because it doesn't match with your figure. So in the figure, the coordinates of point A are XA, YA, and ZA. So here the vector RA is going to be XA times the I direction vector, YA times the J direction vector, ZA times K. Okay, so now using this and then the coordinates of B with this equation, we get that the vector R is equal to XB minus XA. So XB minus XA times I. XB minus XA times I. So the B vector minus A vector will give you R. And the same thing for the Y component, YB minus YA times J. Okay. And that's all there is to it for coming up with a position vector. So that's assuming you know the coordinates of the 2 points. So here we have point A and point B. We know the coordinates. And so the position vector from A to B is given by this equation, B minus A. And now we'll work an example problem. So here we have a cable that we know the connection points. And so we want to find a position vector. So we'll just start off defining the vectors again. So we want to find from A to B. So we want to find R from A to B. And that's equal to RB minus RA. So what we need is the vectors RB and RA. We'll start off with RA. And it is in the, point A is in the XZ plane. So the X component is 1I. And then Z is -3 minus 3K. And then point B is located at -2 in the X direction, 3 in the Y direction, and 3 in the Z direction. So this is how this is a typical scenario in structural architectural engineering, because you know the geometry of the structure. So we would know where these points are located. And so we might have, the Cartesian components already, and we just need to be able to go from the picture, the dimensions in the picture, to the vector representation. So now we have RA and RB, and now we can get the position vector from A to B. And it's B minus A, so -2, -1 in the I, and then plus 3J plus 3, and then this is minus a -3, so go ahead and write that out. Minus -3. Okay. So here's this equation. It's RB minus RA. And again, the useful thing about using Cartesian components is we can just add them all up. So we're adding up the X components. Well, actually, it's subtraction. -2, -1. The same with the J components, 3 minus 0. And then the Z components, 3 minus -3. And what that gives us is the vector from A to B is -3 times the I direction vector, plus 3 times J, and plus 6 times K. So looking at the figure, just check to make sure that makes sense. So we go back in the X direction, and then we go to the right in the Y direction, so that's positive Y, so plus 3, and up in the K direction, because point A is a lot lower than point B, so we're going up a lot. And that gives us the answer, -3, +3, and 6 in the I, J, and K directions. And that's all there is for section 2.7. We'll move on next to forces directed along the line.